So this is a demonstration for the group project for ECGR 3120, where we were tasked with making a inkjet printer like this, where there's two vertical plates separated by 1 millimeter, and they're half a millimeter long, and the total distance is 3 millimeter, and we are giving all these parameters. And today I'll be discussing how I solved part 1, 2, and 3 of this project. So I wrote this project in Jupyter Notebook using Python. I included a pipenv file so that this can be run in a virtual environment. So you just have to run pipenv shell and pipenv install, because we have a pip file which has all the dependencies. So as I run through this, I'll be discussing how I determine all this and how I solve all this. So for this, I'm using matplotlib as my thing to animate it, and over here I just have a bunch of constants like the charge and initial velocity, initial positions, and mass are calculated, and basically just everything that was given and anything that can be calculated very quickly. So in calculating question 1, I assume that there's no gravity, and therefore that there's also no air resistance. So basically the only thing that is going on in the only force that's being applied is the 20 meters per second at the beginning. So this is just a dictionary that stores all the data, and this just goes into a loop. Every 1 microsecond it goes through this, and it does a calculation of the velocity and position. So this doesn't really have an output over here. It just does the calculations, and once you get to this part, this is where it actually draws the parallel place, is where it does the trajectory and also prints out how long it took. So if I run this, a window will pop up. So this is starting at 0 millimeters and it's going to 3 millimeters. So over here is the parallel plates, spaced 1 millimeter apart, and this is the sheet of paper. In this, we can move around, we can look at it, it's all 3D. Zoom in, look at the dot. This dot is to scale. So if we go back, we can see that it prints out how long it took, which is 0.00015 seconds, which lines up perfectly with the calculations, because it's 3 millimeters divided by 20 meters per second, so it lines up. Well, the second question, we're basically drawing a vertical line, which is just the letter I at 300 dpi. So in this case, instead of there only being a force in the x direction, there's also a force in the z direction, or in my case the z direction. I had that plane called the z direction. So to approximate 300 dpi to millimeters, it was found to be about 12 dpmm. I think the actual was 11.8, but I stepped it up to 12. And through calculation and also some, or I guess in this case, I just chose this arbitrary plate voltage. It was calculated, I think the actual calculated for the largest was about 2400, but I'll get to that later. So this just keeps an array of the droplets, because now instead of 1 droplet we need more. I think in this case it was about 60 for 5 millimeter space. So this just creates an array of the dictionaries, and this does the same calculations as before. However, it goes through the voltage and it does the force calculation, and then when it gets to the next droplet, it subtracts a certain amount of voltage to achieve that 300 dpi. So in this case, it was found to be 79. So it gave 12 dpi. and you can see that this is how the velocity is calculated and how the position is calculated. So it's force times how much time's passed divided by the mass plus the previous velocity. That gives like its current velocity, and then the current position is just the velocity times time times 1,000 because unit conversions, and then plus the previous position, and that will give the position z. And in this case, and every single case for this time, position y is always 0 because we have a parallel plate not on that axis, so there's no forces ever on that axis, so it's just going to stay straight on that. And when we get to question 2, this is where it once again plots everything, and it does a animation of one after another parallel, one after another electron, or not, not electron, the printer. So if I run this, it will play the animation more zoomed out because this is to cover the 5mm area that it ends up covering. So if we zoom in a little bit, we can also see how close it's getting to the parallel plates. So this will draw 60 dots, I think was the calculation, and that will create the eye. In the GitHub, there's also videos and GIFs of every single animation. So to speed it up, here's the sped up version of it. So 18 seconds is not the actual time it took to draw that. That was just, well, this is just slow down so that you're able to visualize it. The actual time it took to draw that was 0.009 seconds, and that was with me drawing a 5.34 millimeter long eye. So this, once again, just used Matplotlib to animate this. And for question 3, it was somewhat solved in question 2, drawing the biggest possible eye, because 5.34 was about how big I was able to get it before it started touching the parallel plates and not working. So once again, same stuff applies as before. There's dots per millimeter and the number of droplets needed in an array of the dictionary. And the same calculations are done before, where it's just position, all the positions and all the voltages. And another thing that is kept in mind is the voltage over time, because the third part also wants you to plot a voltage versus time graph. So that is kept in this array. So once again, it is another Matplotlib animation. It draws the same stuff, but this time when the charge is halfway through the capacitor, it will send the next charge through. So that effectively cuts the time down in half. So if I run this animation, it will display 2 different plots. So the one on the left is the trajectory plot, and you'll see how when it reaches halfway between the parallel plates, the next electron gets launched. And then the plot to the right is the voltage over time. So as expected, it's a staircase from 0 seconds to 0.009 seconds. And to show you what the actual animation looks like to the end, I had this pre-rendered. And it videos found that it takes half the time, 0.0045 seconds. And this code is also very adjustable, so if I want to change the plate voltage, I can just change it here, or the step size of the plate voltage or time steps. I could change it to whatever I wanted it to be. And that is my demonstration of the first part of the 3120 project. This is also all on GitHub. On this README, I have also all the information, all the GIFs that I have created from this project. And there will also be a lab report in here once it's written.